Welcome to Tech News Daily. I'm Jane, and I'm here with Oliver. Today is June 15th, 2026, and we have a packed show for you. We're covering 20 major stories, and honestly, they all point to the same direction. AI is moving from the lab into actual infrastructure, and the internet itself is starting to look completely different.
That's exactly it. When we sat down to organize today's stories, we kept seeing four themes repeat. First, the infrastructure layer is maturing rapidly. We're talking frameworks for making brands visible to AI, new agent tooling that's actually production ready, and training foundation models for $1,500. Second, governance is becoming critical because agents are now operating at machine speed, and nobody's figured out safe guardrails yet. Third, enterprise adoption isn't waiting. TCS and Anthropic just announced a partnership, putting Claude into 50,000 employees. And then there's the elephant in the room. Bots now outnumber humans on the internet. That fundamentally changes everything.
Right. And what's fascinating is these aren't separate stories. They're connected. You can't deploy agents at scale without governance systems like Cursor's auto-review. You can't make brands discoverable without understanding how AI search actually works, which is totally different from Google. And you can't plan a GTM strategy anymore without accounting for the fact that half the traffic hitting your site is bots, not people. The economics have flipped.
The economics piece is huge. We have a whole segment later on whether this is a bubble or real infrastructure, but the data is pretty stark. OpenAI hit $20 billion annualized revenue. NVIDIA's data center business is nearly $200 billion, and hyperscalers are spending $700 billion on AI infrastructure. That's not speculation, that's industrial scale build-out. But here's what we're going to dig into today. Which parts are real and which parts are froth?
And for builders specifically, whether you're launching a small AI-assisted business, or evaluating which coding agent to use, or figuring out how to train a custom model without breaking the bank, today's stories have practical answers. We're going from frameworks for discovery to the actual tools you'd use, to governance systems that keep everything safe, to what happens when you try to run agents for days or weeks. Plus, Google DeepMind just published a paper on what comes after AGI that's genuinely thought-provoking.
That paper actually had something weird in it. Summary instructions written for AI readers. It's the first major academic paper that assumes AIs will be reading it. That's the kind of detail that tells you how much has shifted. Alright, we've got a lot to cover. Let's start with the foundations. How AI discovery actually works, and why the frameworks being built right now matter more than most people realize.
So we've been talking about infrastructure, and here's where it gets concrete. There's a new framework circulating in GTM circles called A.G.E.N.T.I.C, and it's basically the playbook for making your brand visible inside AI systems. Not Google, not Bing, I mean Claude, Perplexity, Google AI Overviews. The whole discovery layer has shifted, and most businesses haven't noticed yet.
Wait, so is this just SEO for AI? Because we've been optimizing for search engines for 20 years. What makes this different enough to need a whole new framework?
Great question, and it's the core of why this matters. Traditional SEO optimizes for human scrollable lists. You want to be position 1, position 2, position 3 on a Google results page. But AI search doesn't work that way. An AI system like Claude reads through dozens of sources and synthesizes one answer. It's not showing you a list, it's showing you a single synthesized response. That means the signal AI systems care about is completely different. It's not page rank, it's semantic authority, machine-readable trust that the AI model needs before it will even cite your brand, let alone recommend you or transact with you.
Semantic authority. That's a term I want to dig into. What does that actually mean technically? How does an AI system decide whether to trust a source?
So the A.G.E.N.T.I.C framework breaks it down into 7 phases, and they build sequentially. The first three are foundation. You start with an audit of your current visibility, how many sources link to you, how well your data is structured. Then you graph your entity relationships. Basically, you're telling AI systems not just that you exist, but how you relate to other entities in your industry. Then you equip your content for extraction. This is huge. AI systems don't read prose the way humans do. They need chunked, structured facts. So a product page isn't prose anymore. It's attributes, specifications, reviews, pricing, all machine readable. Once you've built that foundation, you activate with Network and Track. Network means you're connecting into the emerging agentic commerce protocols, OpenAI's Agent Commerce Protocol, Google's Universal Cart Protocol. Track means you're building the measurement layer to see when AI agents are citing you or transacting through you.
Okay, so those are 5 phases. You said 7. What are influence and convert?
Right, so those are the expansion phases. Influence is about building cross-source consensus. If 5 reputable publishers reference your solution, the AI model sees that as stronger signal than just your own claims. You're basically getting external corroboration. And convert is the final phase. It's the agent handoff. You're not just getting discovered, you're making it easy for an AI agent to actually complete a transaction. Open your API, wire up the commerce protocols, make sure the agent can fetch pricing, check inventory, and execute a purchase without human intervention.
So let me synthesize this. A small business launching today can't just build a website, write blog posts, and hope SEO picks them up. They need to think like they're building for machines that will read their data, synthesize it with other sources, and potentially transact autonomously. That's a fundamentally different product design problem.
Exactly. And here's why early adoption matters. Right now, most brands haven't even started on this. They're still doing traditional SEO. So if you audit, graph, equip, and network today, you're ahead of 95% of the market, when Google AI Overviews and Claude start driving more traffic than traditional search. The competitive advantage is in moving fast on the foundation, because once the infrastructure is in place, it compounds. Each phase makes the next one stronger.
So we've talked about the big frameworks and where AI discovery is heading. Now let's zoom in on the actual tools solo builders are using right now. There's a tool that just launched called Agent Browser that's getting traction. And it's a pretty elegant alternative to the standard automation stack like Playwright or Puppeteer.
Agent Browser. I've been hearing about this. What makes it different from Playwright? Because Playwright's pretty well established at this point, and a lot of teams are already invested in it.
Good question. So the key differentiator is that it's built in Rust, not Node.js, which means no heavy runtime dependency. You get a fast command line interface that can run native automation workflows. But here's what's really interesting for LLM-driven automation, is it exposes accessibility tree snapshots with numbered element references. So instead of traditional CSS selectors or XPath, you get references like @E2, @E3. Those numbered references are designed specifically so AI models can interact with them naturally.
That's actually clever. So an LLM doesn't have to pass complex selectors. It just says, click on @E5e, and the browser knows exactly what you mean. Plus, Accessibility Tree gives the AI semantic context about what elements actually do, not just where they are on the page. So you're giving the agent better information about the interface.
Exactly. And there's another layer, it supports semantic locators too, so you can find elements by role, text, or label, which maps to how an AI would naturally think about interfaces. The tool also has a built-in chat mode for natural language control, which is honestly where a lot of this is heading. You describe what you want done, and the agent figures out the interaction pattern.
That brings us to the bigger ecosystem, though. Agent Browser is one piece, but there's also Google's new Colab command line interface and the QwenPaw framework, which are solving a complementary problem. Where Agent Browser handles browser automation, Colab CLI gives you programmatic control over notebooks and compute environments. You can now run Colab from the terminal, automate notebook execution, integrate with CI/CD pipelines, basically turn Colab into headless cloud compute infrastructure.
So that's a shift from Colab as an interactive notebook environment to Colab as scriptable infrastructure. What does that unlock for builders?
Cost-effective GPU access for automation and agent workflows. Instead of spinning up your own cloud infrastructure, you run scripts against Colab's GPUs through the CLI. And then there's QwenPaw, which is an agent framework built in Python that handles multi-provider model integration: OpenAI, OpenRouter, DashScope, DeepSeek, Gemini, all in one interface. So you're not locked into a single LLM provider. You can prototype an agent with OpenAI, swap it to DeepSeek if you want cheaper inference, and your code doesn't break. That's huge for resource-constrained teams.
The multi-provider piece is important because it removes a real vendor lock-in risk. A solo builder or small team can experiment with different models without rewriting authentication and API calls every time. And all three of these tools, Agent Browser, Colab CLI, QwenPaw, they're designed for the same user profile, someone shipping fast who doesn't have time for heavy infrastructure setup.
Exactly. A year ago, to build an AI-assisted automation workflow, you'd need Playwright expertise, cloud infrastructure knowledge, model API familiarity, and honestly, a lot of glue code. Now you have lightweight tools that work together. You're automating browser tasks with accessible AI-friendly selectors. You're running compute on shared infrastructure without managing servers. And you're choosing models based on cost and capability, not what you already wrote code for. For someone building multiple small AI-assisted businesses, which is honestly what a lot of solo builders and small teams are doing, this is a game changer. You can prototype and launch faster.
We've been talking about tools for automation and cloud compute. But there's another layer that's matured dramatically: coding itself. A few years ago, we had autocomplete. Now we have agents that can implement entire features. So, let's map the landscape in 2026. Because there's a real spectrum here, from fully autonomous agents like Atoms and Devin that you point at a task and they ship it, to tools like Cursor and Windsurf that augment your development workflow, to Warp, which is bringing AI into the command line. They're solving different problems.
Right, and this is important because the mental model is shifting. Coding assistants, like GitHub Copilot's autocomplete, that's still about you being in control, writing the code, getting suggestions. But AI teammates, that's delegation. You're telling an agent to implement a feature, refactor a module, write tests, and you're reviewing the result. That's a completely different interaction pattern. So let's break down what we're actually seeing in 2026. On the autonomous end, you've got Atoms and Devin. These are designed to take a task, say, build a login flow with two-factor authentication, and the agent goes end-to-end, writes code, runs tests, handles errors, ships it. Minimal hand-holding required.
That sounds powerful, but I have to ask the obvious question. If the agent ships code autonomously, where's the oversight? How much do you trust that? Because my instinct is that fully autonomous code generation is a ship-to-prod risk if something goes wrong.
That's exactly the right tension. So here's where the cost models tell you something important. Devin, for example, uses a task-based pricing model. You pay per task completed. That creates alignment. The agent is incentivized to solve the whole problem end-to-end because that's how it gets paid. But oversight still matters. The agent can handle straightforward features, a login flow, database queries, API endpoints. It struggles with architectural decisions, legacy codebase quirks, and nuanced product requirements. On the other end of the spectrum, you've got Cursor and Windsurf. These are agentic IDEs. You're still in the editor, still making decisions, but the AI is handling multi-file editing, refactoring, and understanding context across your whole codebase. Cursor Pro is $20 a month. You're paying for the capability, not per task. And the mental model is, this AI is my co-pilot, not my replacement. I tell it what I want, it does the legwork, I verify and merge.
So the cost model actually tells you something about the trust model. Task-based pricing for Devin suggests you're delegating the whole thing. Monthly pricing for Cursor suggests you're still driving but with powerful assistance. What about Warp? How does that fit into this spectrum?
Warp is narrower but interesting. It's specifically for terminal workflows, debugging, system administration, command writing. You describe what you need in natural language, the AI generates the command, you execute it. It's augmentation at the command line. So if you're spinning up infrastructure, troubleshooting deployment issues, or writing complex bash scripts, Warp handles the syntax and edge cases. You're still in control. You see the command before you run it, but it saves the cognitive overhead of remembering flags, syntax, and error patterns. The three tools, Devin, Cursor, Warp, they actually work together in a real workflow. You might use Devin for end-to-end feature implementation on a greenfield service. Then you use Cursor for integrating that into your main codebase and handling the architectural fit. And then Warp helps with the deployment and debugging when something doesn't work. They're not competing, they're addressing different stages of the development cycle.
That's a really useful frame. So the question for a solo builder or small team isn't which agent is best, it's which tool fits which job in my workflow. And that also means the cost doesn't blow up. You're not paying for a full development team, you're paying for strategic leverage at different points. But I want to push on one thing. Cursor and Windsurf, they feel pretty similar from the outside. Both agentic IDEs, both integrated into your existing editor. What's the actual differentiation?
Good question, and it's worth digging into because this is where the tools are still rapidly evolving. Cursor has tighter Claude integration right now, which gives it strong context understanding and multi-file refactoring. Windsurf emphasizes what it calls flow mode, a more continuous, less interruptive agentic experience. Some developers prefer Cursor's explicit control points, others prefer Windsurf's flow. Honestly, they're converging. The platforms are iterating fast. But the key insight for someone building multiple small bets is, lock-in isn't as bad as it used to be. You're not choosing between a lifetime of Cursor or Windsurf. You can use Cursor for one project, try Windsurf for another, keep what works. The integration with your codebase is standard, Git, LSP, whatever, so switching isn't painful. That's different from choosing a cloud provider or database where switching is expensive.
So we've talked about coding agents that can ship features autonomously. But here's the hard question. If an agent is operating at machine speed and can execute code, modify files, push to production, how do you prevent it from breaking things? Because telling an agent be careful doesn't scale. You need actual governance infrastructure.
Exactly. And this is where Cursor's auto-review system gets interesting, because it solves the problem in a really clever way. Most people's instinct is to use binary gates. Either the agent can do something, or it can't. You whitelist certain operations, blacklist others. But that doesn't work in practice because the same command can be safe or dangerous, depending on context. Deleting a file is catastrophic if it's your only copy of important code. It's fine if it's a temporary build artifact. So auto-review doesn't use binary gates. It uses contextual risk assessment.
Contextual? Meaning the classifier looks at the situation before deciding whether to allow or block? How does it even have that information? And more importantly, can it be fast enough to not become a bottleneck for agent speed?
Great questions. So auto-review is itself a specialized AI classifier, a small, fast model designed specifically to evaluate risk. And here's the key. It's not just binary yes or no. It can actually inspect the workspace. The classifier can read files, grep for patterns, understand what code exists, before saying yes to a deletion or modification. It runs in the same RPC stream as the parent agent, so latency is minimal. The architecture keeps it tight and responsive.
So it's an AI evaluating what another AI is about to do, and it's getting the context it needs to make a smart decision. That actually makes sense. But let me ask the operational question. If the classifier blocks an action, what happens then? Does the whole agent stop? Does it escalate to a human?
This is where the feedback loop is elegant. When the classifier blocks or questions an action, it sends that reasoning back to the parent agent. And in most cases, we're talking 7% of total chats, the agent can self-correct. It understands why something was risky and adjusts its approach without user interruption. For the clear-cut cases where something genuinely shouldn't happen, only then does it escalate to the user. But remember, that's rare because allow lists and sandboxing handle the vast majority of operations. The classifier is only really judging ambiguous cases. Across testing, the classifier blocks only about 4% of reviewed actions.
4% blocked, 7% requiring user interruption. Those are really low friction numbers. That suggests the system has been tuned to minimize false positives. How'd they actually build confidence in those numbers? Because if you're training a classifier to make safety decisions, you need to validate it on real data, not just synthetic cases.
They evaluated it against 6,122 labeled rows from actual internal sessions, real developers, real workflows, real risks. They tested it against synthetic adversarial cases too, to make sure it's not just memorizing patterns. The eval measured classification consistency and what they call flapping, where the classifier keeps changing its mind about the same action. Once you've validated at that scale with real data, you get confidence that the system works in production.
That brings us to the bigger picture. Why does this matter for scaling AI agents? I mean, if I'm building an autonomous agent to manage my codebase or infrastructure, I need to trust that it won't accidentally break things. But I also don't want a human reviewing every decision. This auto-review architecture solves both problems, doesn't it?
Exactly. It's the missing piece between capability and deployment. You can have an incredibly capable agent, but if every action requires human review, it becomes a bottleneck. If you give the agent completely free rein, it becomes a liability. Auto-review sits in the middle. It lets low-consequence operations proceed freely. It catches genuinely dangerous moves, and it gives the agent enough autonomy to be useful without creating chaos. As agents start managing more complex workflows, testing frameworks, deployment pipelines, code-base refactoring, this kind of contextual governance becomes critical infrastructure. It's what lets solo builders and small teams actually delegate to agents without staying up at night.
We've been talking about governance systems that keep agents safe and responsive in the moment. But there's a bigger problem nobody really talks about. What happens when you need an agent to work for hours, days, or even weeks? Most LLMs have context windows that fill up. Sessions end. The agent loses track of what it was doing. So how do you actually build agents that can maintain focus and progress over extended periods?
This is one of the most interesting engineering problems right now. And here's the thing. It's almost entirely an infrastructure problem, not a model problem. The core innovation isn't a bigger context window or a smarter model. It's externalizing state to disk. Think about how a human handles a multi-day project. You write things down, you keep a journal, you have a task list, you review what you did yesterday before continuing today. You don't try to hold everything in your head. Agents need the same pattern.
So you're saying the agents that work for days or weeks aren't working because they're smarter, they're working because they have notebooks, like literally writing their thoughts and progress to files.
Exactly that. There's a pattern practitioners have converged on called the Ralph loop. It's beautifully simple. You have a few key files that live outside the agent's context window. A product requirements document, prd.json, that defines the task. A progress.txt file that logs what's been done, what's blocked, what's next. An A.G.E.N.T.I.C file that documents the agent's instructions and rules. Then, each session, the agent reads those files first. It understands the baseline. It can see the full history. It can pick up exactly where the previous session left off without losing coherence.
That's actually elegant. But I'm hearing an implication. If state lives on disk and the agent reads it at the start of each session, the agent's still limited by whatever it can fit in its context window when it starts, right? So you can have a 1-month project, but you can't fit the entire 1-month history into a single session. How does the agent stay coherent across that?
That's where you hit the real wall, and it's called context rot. It's not about hitting token limits, it's about information decay. Here's what happens. An agent works for 24 hours straight, context window filling up with every task, every thought, every error. Performance degrades, not because it's out of tokens, it usually has room, but because the signal-to-noise ratio gets horrible. The agent has 16 hours of debugging logs, dead-end explorations, and corrected mistakes mixed in with current state. The model struggles to maintain focus. So you don't just manage token count, you actively curate what the agent sees each session. You compress history. You keep only the essential lessons learned and current state.
So context rot happens well before token limits hit. That's the key insight. You can't just write longer context windows and hope that solves multi-session agency. You have to actively manage what information flows into each session. What's the evidence this actually works? Because I'm hearing theory. I want to know if agents have actually sustained work over extended periods and what that looked like.
We have concrete examples. Anthropic's Claude worked autonomously on coding tasks for over 30 hours. That wasn't because Claude suddenly got a 1,000-hour context window. It was rigorous session management, saving state between runs, contextualizing each new session with essential priors, letting Claude focus on the next increment of work. And then there's Project Vend. This was an experiment where an AI agent ran a physical vending business for an entire month. The agent had to manage inventory, handle customer transactions, debug mechanical failures, and adapt its strategy based on real outcomes. Month-long autonomy, but it surfaced problems you never see in simulated environments.
Wait. Project Ven ran for a month? That's not just long running. That's actually managing a real operation, with real constraints and real consequences. What kinds of failure modes showed up that wouldn't in a simulated environment?
The real world is messier than any simulation. The agent had to handle edge cases nobody anticipated, mechanical jams that required physical inspection, customers doing unexpected things, inventory depletion scenarios, pricing decisions with real economic consequences. Running for a month meant the agent had to learn from mistakes in real time, adjust strategies based on actual feedback, and maintain coherence across multiple failure modes happening simultaneously. That's where you discover whether your harness engineering actually works. A 24-hour lab test might pass. A month in production reveals brittleness.
So here's my next question. When a session breaks, maybe the agent crashes, maybe a task gets too complex and the agent gets stuck, how does recovery actually work? Because if your externalized state on disk, you can technically resume, but can the agent understand what went wrong and pick a different approach?
Recovery is where the harness design really matters. When the agent starts a new session, it reads the progress log and sees attempted solution A yesterday, failed, reason was timeout on API call. So the next session doesn't just resume, it resumes with context about why the previous approach didn't work. The agent can try a different strategy. You can even add a failure mode file that documents known blockers and alternate approaches. The agent learns from its own experience across sessions in a way that pure model capability alone never could. It's not about the model getting smarter, it's about externalizing a memory system that the model can read and learn from.
So the breakthrough here is really about engineering, not model capability. You're building infrastructure that gives agents memory and task continuity. But I want to zoom back out. For someone launching AI-assisted businesses, What does this actually unlock? Because Project Vend is a cool experiment, but what's the practical use case?
Several things become viable that weren't before. Long-running trading bots that learn from market moves across days and adjust strategy. Ongoing code-base refactoring tasks that work incrementally without needing constant human oversight. Persistent research agents that compile information over weeks and surface patterns you'd miss in a single session. Background business monitoring, an agent that runs continuously, checking system health, customer metrics, competitive signals, and alerts you only when something material changes. For someone building multiple small bets, a background agent running for days or weeks costs almost nothing compared to hiring a human analyst. And the infrastructure, the state files, the Ralph loop pattern, it's simple enough that a solo builder can implement it.
That actually changes the economics of automation. Right now, most AI agents are conversational. You ask a question, you get an answer, interaction ends. But if you can run agents for days or weeks with relatively simple infrastructure, you can build genuinely autonomous systems that work in the background. The key constraint isn't the model anymore, it's whether you've engineered the harness correctly.
Exactly. And that's the counterintuitive finding from all this. The next breakthrough in agent capability isn't waiting for a smarter model, it's better engineering, better state management, better recovery mechanisms, better ways to curate what information flows into each session. A 7 billion parameter model with a well-designed harness can outperform a much larger model running without proper state management. That's why builders are getting traction now, instead of waiting for the next quantum leap in model performance. The leverage is there if you build the infrastructure right.
One of the bigger announcements this week came from TCS, Tate Consultancy Services, and Anthropic. TCS just announced they're deploying Claude across 50,000 employees in 56 countries. But here's what makes this different from just another enterprise licensing deal. They're not just buying seats. TCS is becoming what Anthropic is calling Customer Zero for regulated industries. They're testing internally, working through the real implementation problems, then packaging Claude into industry-specific solutions.
This is actually huge. TCS isn't a startup tinkering with AI. They're a massive global systems integrator with deep expertise in regulated industries, banking, insurance, healthcare, telecom. When a company like that says, "We're deploying Claude at scale," it signals something important. Claude works reliably enough for the kinds of high-stakes workflows where mistakes cost money or violate compliance rules. What specific use cases are they already running?
They've already announced 3 concrete implementations. Diligenta, their insurance platform, is using Claude for claims processing across 22 million policyholders. Then there's lending advisory, Claude handling analysis for credit decisions, and policy management workflows. What's interesting is the pattern. These are all domains where accuracy matters enormously. A wrong decision on a claim denial or a credit recommendation doesn't just frustrate a customer, it creates legal liability.
Claims processing is the perfect test case for AI at scale, actually. You have massive volume, millions of claims, so even small efficiency gains compound into significant cost savings. But claims are also incredibly document-heavy. You need to extract information from medical records, doctor's notes, policy documents, all in different formats. And if the AI makes a mistake, you're paying out wrong amounts or denying valid claims. An insurance company can't just say, "The AI made an error." There's regulatory oversight, customer complaints, potential litigation. So if Claude is handling that at scale, for 22 million policyholders, that tells you something about its reliability in messy, real-world conditions.
Exactly. And that brings me to the customer zero angle. TCS isn't just testing Claude. They're documenting every integration challenge, every compliance requirement, every edge case. They're building playbooks internally. Then they package those learnings into industry-specific solutions they can sell to other banks, insurers, healthcare systems. So TCS solves their own problem, figures out how to do it at scale, and then monetizes that knowledge. That's a really smart GTM model for Anthropic too. Instead of trying to sell directly to every regulated industry, Anthropic works through TCS, who understands the regulatory landscape intimately.
And that's where the real enterprise AI money flows. Not in consumer chatbots. It's in regulated industries, where you have massive document processing backlogs, high compliance costs, and economies of scale. TCS also announced they'll certify 50,000 employees on Claude best practices through their training arm, TCS ION, particularly across India. That's not just employee training, that's building a massive network of practitioners who know how to deploy Claude in regulated environments. When a bank wants to implement Claude for lending decisions, TCS has 40 consultants in that bank who've already been trained. That's the leverage that drives enterprise adoption.
So we're looking at enterprise AI adoption, where the differentiation isn't raw capability anymore. It's reliability, auditability, and compliance infrastructure. Regulated industries don't care if Claude can write poetry. They care whether Claude can extract medical information correctly 99.99% of the time, and whether it creates audit trails that regulators will accept. Does the partnership address that explicitly?
That's built into the whole TCS approach. They're not just deploying Claude, they're deploying Claude with governance layers, audit logging, compliance frameworks. The insurance claims case is telling. Diligenta isn't using Claude as a fully autonomous decision maker. It's using Claude to extract facts, summarize documents, flag edge cases for human review. The human stays in the loop for final decisions, but Claude handles the work that would normally take a human analyst hours. That's the sweet spot for regulated industries. AI augmentation, not automation. And because every interaction is logged and traceable, regulators can audit the exact workflow, what information went in, what Claude generated, what decision was made, why. That auditability is worth billions to financial institutions.
So the real competitive advantage for TCS here isn't just having access to Claude, it's having worked through all the hard compliance and integration problems before anyone else. By the time competitors realize this is happening, TCS will have already packaged solutions that integrate Claude with their existing systems, banking platforms, insurance platforms, healthcare systems. Switching costs become high because you're not just switching Claude, you're ripping out entire integrated workflows.
Exactly. And this signals something important about where enterprise AI money actually flows in 2026. It's not going to startups building cool demos. It's going to systems integrators and consulting firms that can credibly promise to implement Claude or any frontier model reliably in production across thousands of employees. That's where TCS wins. They have the scale, the regulatory expertise, the existing relationships with enterprise IT departments, and now they have the Claude deployment playbook. That's a defensible moat. All right, so this next story genuinely surprised me when I read it. A team at Sapient just published results showing they trained a full foundation model, not fine-tuned, not distilled, a 1 billion parameter model from scratch. And here's the part that should break conventional wisdom. They did it for about $1,500 in compute costs.
$1,500? That's pocket change compared to what we usually hear about training foundation models. Meta trains models for hundreds of millions. OpenAI's infrastructure spend is in the billions. How is that even possible? Are we talking about a model that barely works, or is there actually something here?
No, this actually works. The model is competitive with much larger open models on standard benchmarks. The trick is they didn't use the traditional training pipeline. Instead of pre-training on trillions of tokens of raw internet text, which is massively expensive, they trained exclusively on curated instruction response pairs, 40 billion tokens total, all high-quality examples of tasks and solutions. They eliminated the noise.
So they're trading raw scale for signal density. Less data, but higher quality. That reduces compute, because the model isn't wasting cycles on learning internet garbage. But I'm still confused about the architecture itself. If it's 40 billion tokens instead of multi-trillion, you're still hitting optimization challenges, right? How'd they solve the stability problems?
This is where the real innovation lives. They use an architecture called H.R.M.T.I.C, Hierarchical Recurrent Model. Instead of a standard transformer, they separate computation into two layers. There's a slow H module that handles semantic context, the big picture meaning of what's happening, and then a fast L module that handles local refinement, the specific tokens and syntax. By separating these concerns, they prevent mathematical instability that normally shows up when you train recurrent models on language tasks.
Wait, recurrent models on language? I thought recurrence was dead for language after transformers showed up. Why go back to recurrence if you're trying to be efficient? Doesn't that create new problems?
Good question, and that's exactly why the architecture matters. Pure recurrence struggles with language because you lose long-range context. Each token only sees a limited window. Transformers solve that with attention, but at massive computational cost. HRM-Text splits the difference. The H module is recurrent, but operates at a semantic level, so it can maintain long-range meaning without processing every token. The L module handles the local token work efficiently. They also introduce something called magic norm, specialized normalization that stabilizes the recurrent loops during language training. And they use a warm-up procedure where they progressively increase the depth of the model instead of starting from full depth, which helps convergence.
Okay, so the architecture's clever, the data is curated instead of raw, and the training procedure is carefully staged. But here's the practical question. You trained a 1 billion parameter model for $1,500. That's incredible cost efficiency. But can it actually do real work? Or is it a toy that benchmarks well but fails in production?
That's exactly why this matters. The performance is competitive with open models that are much larger and trained for much more. We're not talking about a 10 times improvement in efficiency here. We're talking about making custom foundation models accessible to organizations that can't afford multi-million-dollar training runs. Imagine you're a hedge fund with proprietary trading data. You can't send that data to OpenAI or Anthropic for training because you can't compromise secrecy. But for $1,500, you could train your own foundation model on 40 billion tokens of your internal trading signals, market analysis, news interpretation. Or imagine you're a bank. You could train a model specifically on your internal compliance documents, regulatory requirements, customer interaction patterns. Something customized to your exact domain and vocabulary that a generic model could never match.
That's a massive competitive advantage. A bank using a custom model trained on their internal data versus using a generic LLM that doesn't understand their specific workflows. The custom model would be better at their specific job, even if it's smaller overall. But I want to push on feasibility. $1,500 is cheap, but that's still compute, cloud GPUs, whatever. You need infrastructure to run this. Can a solo builder or small team actually do this? Or do you need specialized ML expertise?
This is the democratization part. The Sapient team published their approach and architecture. The code and methodology are reproducible. You don't need a PhD in deep learning. You need someone who can set up a training run, load data, configure hyperparameters, monitor training loss. That's intermediate ML engineering, not cutting-edge research. And for $1,500 on cloud GPUs, it's accessible to any bootstrapped startup or small team with a specialized use case. $1,500 is within reach if the model creates even modest value. That's a completely different calculus from needing millions up front.
So we're talking about a fundamental shift in who can build foundation models. Up until now, foundation model training was a capital-intensive business. It required billions in infrastructure and compute. But if you can train a competitive model for $1,500 using curated data, the barrier to entry drops dramatically. What does that mean for the existing players like OpenAI and Anthropic? Do they suddenly lose their moat?
Not entirely, but it's interesting. OpenAI and Anthropic have advantages in scale. They have access to much more data, more compute, more trained researchers. Their models will continue to be frontier models. But this does mean they can't rely solely on being the only option anymore. If you're a specialized organization, a trading firm, a medical research lab, a bank, and you have proprietary data, the value of training your own model is becoming real and affordable. You're not competing with OpenAI on general capability. You're building something better for your specific use case. That's a different competitive dynamic than, can I afford to use the latest frontier model as a service?
That circles back to something we've been talking about all episode. The architecture of AI infrastructure is changing. We started with frameworks like A.G.E.N.T.I.C for discovery, then tools for automation, then governance systems for agents. Now we're at a point where someone can train a custom foundation model affordably. Put those all together, custom models plus agents plus governance, and you get a pretty complete stack for building AI-assisted businesses. For a solo builder or small team launching multiple ventures, that's incredibly powerful.
Exactly. A year ago, if you wanted to launch an AI business, you had to build on top of an external LLM, Claude, GPT, whatever. You were dependent on their pricing, their uptime, their policy changes. Now, you can train a model tailored to your domain for $1,500. Combine that with the agent infrastructure we talked about earlier, and suddenly, you have genuine independence. You're not at the mercy of a single LLM provider. You can iterate your own models based on your business's specific needs. For cash-constrained builders, that changes everything.
All right, so we've talked a lot about building AI infrastructure and deploying agents at scale. But there's a story that cuts through all of that and changes the fundamental economics of the internet itself. Cloudflare just released data showing that bots now account for 57% of all web requests. For the first time in recorded history, machines outnumber humans in the machine-readable layer of the internet. That's not incremental. That's a phase transition.
Wait, 57%? I want to make sure I'm understanding this correctly. Are we talking about good bots, like search engines indexing, or is this including malicious bots, scrapers, security threats?
Good question. This is mostly traffic, so it includes all of it. Search engine crawlers, security scanners, malicious bots. But the important subset is AI-powered bots. Answer engines, autonomous agents, crawlers that feed AI systems. Those are the bots that are fundamentally different from previous generations. Previous bots just indexed and returned links. Modern AI bots read, understand, synthesize, and now they're starting to transact. So yes, 57% includes noise, but the signal, the AI-driven portion, is the part that's reshaping everything.
That's the key distinction. And what that means is the internet's original architecture, built around human visitors clicking through to websites, is obsolete. Right now, not in theory. We're seeing the consequences in real time. Publishers are panicking because traffic is collapsing. Google's own AI Overviews feature is reducing click-through rates by roughly 50%. People get the answer directly from Google without ever visiting the source site. That's half your traffic gone.
And it's not just Google. We're seeing reports of publishers experiencing traffic drops of 30 to 50% across the board as AI agents and answer engines proliferate. Business Insider reported losing half their search traffic. That's a publication with serious editorial capacity, and their entire business model is premised on search traffic. Now that mechanism is disappearing.
The scary part is speed. This happened faster than anyone predicted. We were expecting this transition around 2027. It's 2026 and it's already here. And it's not just consumption anymore. Autonomous agents can now browse, shop, and complete transactions. They're not just reading information, they're making economic decisions and moving money. That completely changes the security model and the architecture you need.
Right. And to manage that, the industry is starting to create new protocols. One that's emerged is HTTP 402, a paywall protocol specifically for machine access. The idea is human visitors get your content freely. AI crawlers encounter a paywall and have to pay to access or republish information. It's designed so site owners can monetize bot traffic instead of just getting cannibalized by answer engines.
But HTTP 402 only works if it becomes standard and enforced. Right now, if you implement it, most AI crawlers just ignore it or bypass it. We saw research showing that standard bot detection only catches 1 of 7 AI agents. They're too smooth. They mimic human behavior so closely that traditional blocking fails. So paywall protocols sound good in theory, but enforcement is the real problem.
Which brings us back to the economics. You have 3 categories of web traffic now. Humans, the smallest and least efficient group. Search engine bots, still important for discovery, but increasingly replaced by direct answer engines. And AI agents, the fastest growing, most efficient, and increasingly autonomous. If you're building a website or an AI-assisted business, you can't optimize for humans anymore. You have to optimize for all 3, but especially for machines.
And that changes GTM strategy fundamentally. Let's say you're launching an AI-assisted business in 2026. You still need a website for human customers. But you also need to think about how AI agents will discover you. Will they find your pricing automatically? Can they fetch your API documentation? Can they complete a transaction? You're not just building for eyeballs, you're building for autonomous consumption by machine agents.
Earlier in the episode, we talked about the A.G.E.N.T.I.C framework, making your brand visible and transactable within AI systems. That wasn't theoretical. It was responding to exactly this. The internet is shifting from human traversable to machine consumable. If you don't optimize your business for AI agents, you're already behind.
And for solo builders, this is actually an opportunity if you think about it right. You don't have massive traffic volume to protect. You're building something new. You can native build for bot-first economics from day one. Instead of thinking, how do I get humans to find me? Think, how do I make sure AI agents cite me, recommend me, and send customers to me? That's a totally different design problem, but it's solvable. And if you solve it early, before competitors catch on, you've got a genuine advantage.
So here's the practical version. If you're building an AI-assisted business, serve your data as structured information that AI can extract and reason about. Make your API accessible and documented so agents can integrate. Support agent-driven transactions. Don't rely on search engine traffic because that mechanism is collapsing. Instead, earn citations from answer engines and agent-to-agent recommendations. The winners in 2026 are going to be the people who stopped optimizing for humans and started optimizing for machines.
Okay, so this next paper is genuinely unusual. Google DeepMind just published a 57-page research paper on what comes after AGI, the Pathways to Artificial Superintelligence, or ASI. And the first thing you notice when you read it is there are summary instructions written for AI assistants. This is the first major academic paper that explicitly assumes AI systems will be reading it. Think about what that signals.
Wait, they wrote instructions for AIs reading the paper? That's not typical for academic publishing. Why would they do that? I mean, technically an AI could read any paper, but explicitly writing for AI readers is almost like they're treating the AI as a peer reader instead of just a tool someone uses to summarize.
Exactly. And that's the meta signal. We've crossed into a phase where the primary audience for frontier research isn't just human researchers anymore. AIs will read this paper, understand it, potentially build on it. That implicit assumption that AIs are now readers, not just subjects, tells you how much the conversation has shifted. But here's the actual content. The paper reframes AGI completely. They don't treat AGI as the finish line, they treat it as the starting point.
Okay, so that's a conceptual shift. AGI was always supposed to be the holy grail, human-level AI across most cognitive tasks. But they're saying that's just the beginning? Walk me through how they actually define ASI versus AGI.
So AGI, they define as median human-level performance across most cognitive tasks. That's the baseline. But ASI, artificial superintelligence, is defined much more specifically. It's systems that can outperform tens of thousands of coordinated human experts working together for a decade. That's not just better, that's a different magnitude of capability. One person can match a human. ASI can match a coordinated expert civilization.
That's a crazy specific definition. Tens of thousands of experts for 10 years. Why not just say, smarter than all humans? Why that particular frame?
Because they're trying to be precise about coordination and time. A single human is fast, but limited in knowledge and capability. Tens of thousands of experts coordinated over a decade represents the best collective human capability we can demonstrate empirically. It's not theoretical, it's measurable, and it's a much higher bar than individual human intelligence. The paper then lays out 4 pathways to get from AGI to ASI.
4 pathways. Okay, I'm ready. What are they?
First is pure scaling. Just keep increasing compute, data, model parameters. The assumption is that scaling alone will eventually hit ASI capabilities. Second is algorithmic paradigm shifts. Maybe transformers get replaced by something fundamentally better. A new architecture that's orders of magnitude more efficient. Third is recursive self-improvement. The AI system improves its own training process, which creates better systems, which improve their training further. Exponential improvement. And fourth is multi-agent collectives. Instead of one giant system, you have millions or billions of specialized agents that can coordinate instantly and share knowledge perfectly.
Those are 4 very different paths. The first is just throwing money at the problem. The second is waiting for a breakthrough we can't predict. The third sounds like it could accelerate or spiral. But the fourth one, multi-agent collectives, that's interesting because it assumes coordination is easier than building capability. Are they saying that's the most likely pathway?
They're careful not to rank them by likelihood, but they do note that the fourth one might be the most underrated. Here's why. The paper specifically says that 100 million AGI instances, individual human-level AI systems, with instant knowledge sharing, could themselves constitute ASI. They'd share information perfectly, coordinate instantly, have zero communication overhead. A human-coordinated group takes meetings, writes emails, has delays. 100 million AIs with perfect coordination and instant knowledge sharing? That's a different animal. And the cool part is, technically, you could already build that if you had enough GPU access and wanted to pay for it.
So pure coordination of existing capability could already achieve ASI without waiting for scaling or breakthroughs? That's a sobering thought. But I have to ask, the paper also talks about frictions that could slow all of this down. What are the actual constraints they identify?
6 major ones. First is the data wall. Training data is finite and increasingly exhausted. You can't scale infinitely on data if you've already consumed internet-scale information. Second is resource constraints. Compute, energy, land for data centers. Building enough infrastructure to push toward ASI is enormous. Third is paradigm insufficiency. Maybe transformers are actually close to a theoretical ceiling, and algorithmic improvement hits a wall. Fourth is research difficulty. The problems to solve might just get exponentially harder as you approach ASI. Fifth is abstraction barriers. AIs learn from human abstractions and might not be able to discover fundamentally new conceptual frameworks that humans haven't shown them. And sixth is political slowdown. Governments might deliberately regulate and slow deployment.
So you've got technical frictions, infrastructure frictions, and political frictions. And they're not assuming any single one is insurmountable, but they're asking, what combination slows progress most? That's honest. A lot of people just assume scaling continues exponentially forever, but this paper says the physics and politics might not cooperate.
Right. And they're explicit about one thing. ASI is still constrained by physics. It's not omnipotent. It has to run on actual hardware, use actual energy, process information at actual speeds. You can't build a superintelligence that violates thermodynamics or the speed of light. That's not poetic. That's an important constraint. It means even ASI has limits.
So coming back to the multi-agent collective pathway, since you flagged it as underrated, what does that actually look like in practice? If you had infinite resources and wanted to build ASI through agent coordination, what's the architecture?
The paper doesn't spell out a full architecture, but the implication is specialized agents. 1,000 agents that are experts in mathematics, 1,000 in physics, 1,000 in software engineering. Each agent is trained and optimized for its domain. They all run in parallel. When one agent encounters a problem it can't solve, it broadcasts the problem to other agents. They coordinate on the solution. Then the solution gets shared instantly to all agents who might benefit from that knowledge. With perfect coordination, no communication overhead, and instant knowledge sharing, the collective can handle problems none of the individual agents could. And because it's digital, you can run millions of instances. Scale the collective.
That's actually less like a single superintelligence and more like a digital civilization. Millions of specialized entities coordinating perfectly. And if you think about it, that's almost within reach now. You could prototype it on a smaller scale. You could build 100-agent collective right now, see if the architecture works, then scale up. That's different from waiting for the next breakthrough in model capability.
Exactly. Which is probably why they flagged it as underrated. It doesn't require waiting for theoretical breakthroughs or new architectures. It's an engineering problem. Given existing models and enough compute, you could start building multi-agent collectives today. That's different from the other three pathways, which are either dependent on luck, finding a better algorithm, or hitting hard physical limits.
So if I'm a builder launching AI-assisted businesses, which of these pathways matters most for me? I'm not trying to build ASI. I should care about this paper because
understanding the timeline and the likely pathways helps you position your bets. If pure scaling hits a data wall sooner than expected, the competitive advantage shifts to whoever has proprietary data or better algorithms. If multi-agent collectives work and become the dominant approach, that changes what infrastructure you want to build on. Plus, remember we talked earlier about training a foundation model for $1,500. That becomes way more valuable in a multi-agent collective world. You're not trying to build one giant superintelligent model. You're building specialized models that coordinate. That's actually more accessible than trying to scale to massive monolithic models.
So the paper is signaling the next era might not be about bigger and bigger single models. It might be about orchestrating many smaller specialized models. That's a different competitive dynamic, and it's one where smaller teams and bootstrap builders have more leverage, because you can build a specialized domain model for $1,500. The hard part becomes coordination and orchestration, not raw capability. That's infrastructure and engineering, not infinite capital.
Precisely. And that's why this paper matters right now. It's not just theoretical speculation about what ASI looks like. It's reframing the competitive advantage in the next phase of AI development. The winners might not be whoever builds the biggest model. They might be whoever figures out how to coordinate specialized models effectively, manages the frictions best, and navigates the political constraints. That's a different game than the one we've been playing for the last few years.
So we've been dancing around a question all episode that basically every tech investor and strategist is asking right now: is AI a bubble? Because the stock prices have corrected. There's been a real pullback in valuations. Some of the hype has deflated. Does that mean the underlying technology is hype too, or is this something else?
This is the key question, and honestly, I think the answer is it's neither completely a bubble nor completely validated. But the data tells a specific story. OpenAI wasn't even a revenue business a few years ago. Now they're running at $20 billion in annualized revenue. That's not projection, that's actual money flowing in from customers. That's not hype, that's traction.
Okay, 20 billion annualized is real, but OpenAI is one company and they're not publicly traded. So we don't have the market pricing in real time. What about the companies we can actually measure? Where's the demand signal showing up most clearly?
NVIDIA. Look at their data center business. They just reported $193.7 billion in fiscal 2026 data center revenue. That's not a startup projecting growth. That's a massive established company selling physical hardware, chips, GPUs, at a pace that's accelerating, not stabilizing. If AI demand was fake, NVIDIA's revenue would be collapsing. Instead, it's the fastest growing segment they have.
Fair point. But NVIDIA benefits from any compute demand, not just AI. They sell chips for data centers, gaming, automotive. How much of that 193.7 billion is actually driven by AI versus general cloud growth?
The vast majority is AI. Their fiscal results literally break it out. Data center revenue is driven by AI accelerators and networking for training and inference. Gaming and automotive are smaller pieces. The company is transparent about that. But here's what really matters. The hyperscalers, Google, Microsoft, Amazon, Meta, they're spending roughly $700 billion collectively on AI infrastructure right now. That's not cautious spending, that's aggressive. And they're running into capacity constraints, not demand constraints. They want to spend more. They literally can't. The chip factories can't produce fast enough.
Okay, so capacity constraints mean demand is real enough that you can't even build supply fast enough to meet it. That's a bullish signal. But I want to dig into the economics. The stock market is saying, we're not sure this is profitable at scale. So what's changed about the profit dynamics that makes the market skeptical even though demand is accelerating?
This is where inference economics matters. For the last 2 years, the focus was training models. You build the model once, that costs a lot, then you run inference cheaply for millions of users. Chatbots fit that model. One question, one answer, you move on. But agents change the equation completely. An agent doesn't ask one question. It loops. It plans. It refines. It runs hundreds or thousands of tokens per task. A trading agent might generate millions of tokens working through market analysis, executing strategies, monitoring positions. That's sustained compute demand. You can't amortize training cost anymore. You need constant inference infrastructure.
So the profit challenge isn't that AI doesn't drive demand. It's that agents as customers require more compute per customer than chatbot as product. That means operating margins might be lower than people expected. Is that the issue? Or is it something else?
It's both that and the realization that inference at scale is a margin business, not a high-margin business. You're competing on cost per token. You need to optimize hardware, optimize inference speed, optimize power consumption. The winners will be whoever can run inference most efficiently. That's fine, it's still a business. But it's not venture scale returns, it's more like chip manufacturing returns. Actually, it is chip manufacturing. Tokens require physical infrastructure. They require chips, they require memory, they require power plants, cooling, land, workforce to manage data centers. The whole stack has shifted from software, which scales for free once you build it, to hardware, which requires constant physical investment.
That's the real shift then. People were thinking about AI like they think about software companies. Build it once, deploy globally, margins expand. But you're saying the economics are flipping back toward industrial manufacturing models because tokens require actual atoms and energy.
Exactly. And that means the stock market's caution might be rational. If you're a venture investor looking for a 10x return, AI infrastructure looks like a bad deal. You're competing with capital-intensive hardware companies that have 5 to 10-year payback periods. But if you're a sovereign wealth fund or an industrial investor looking for steady long-term returns, this is incredibly attractive. You're building the foundational infrastructure for the next computing era. Governments are even getting involved. The UK announced $1.1 billion in investment in AI hardware. That's not venture capital, that's industrial policy.
Okay, so we're looking at the stock correction as a repricing based on realistic assumptions about margins and capital intensity. The demand is real. Nvidia's revenues are real. OpenAI's growth is real. But the valuations were priced assuming higher margins and faster scaling. Does that tell us anything about which parts of the AI stack are actually good businesses versus which parts are hype?
This is where the historical parallels matter. When railroads were built in the 19th century, massive capital was required. The returns were real. They transformed commerce and communication. But many railroad investors lost money because the industry was crowded and margins compressed. The technology succeeded. Most of the investors lost money. Fiber optic cables, same thing. Laid billions in fiber, technology succeeded. Most of the companies that laid it went bankrupt or got acquired at terrible valuations because the margins were lower than people expected. So the question isn't, is AI real? It's which layer of the stack becomes commodity and which layer holds margins. The answer seems to be the infrastructure commoditizes chips, power, data centers. The differentiation moves to the software layer, models, agents, applications. That's where you want to position yourself.
So, if I'm building an AI-assisted business, I should not be trying to build custom chips or run my own data centers. I should be building on top of that infrastructure, expecting it to become cheaper and more accessible. But I should be building proprietary software, models, or applications where I have defensibility. Is that the right read?
That's the smart read. Or if you do want to go infrastructure, you need to be genuinely differentiated, like quantum computing or new chip architectures. But if you're a solo builder or small team, you're not competing with TSMC or Samsung on chip manufacturing. You're building applications and workflows that create value for customers using commodity infrastructure. Early on, you're probably using API access to Claude or GPT. As you mature and have data leverage, you might fine-tune or train custom models, but you're not starting with infrastructure. That's enterprise-scale capital.
Last question on this. The market correction. Stocks are down, some valuations have been repriced. Does that signal the bubble is deflating? Or is it just a normal pullback in a maturing technology cycle?
I'd call it a repricing from speculative froth to realistic industrial build-out. The technology is not being questioned. Demand is not being questioned. What's being repriced is expectation of growth rates and margins. That's healthy. It's the market doing its job. The companies and investors positioned for steady, long-term infrastructure returns will do fine. The speculators who bought on the assumption of venture-scale returns are being disappointed. But that's market sorting. It doesn't mean AI is a bubble. It means the easy money has been made, and the hard work of building real businesses begins.
So for someone building right now, the message is, understand which layer of the stack you're playing on. If you're infrastructure, you're competing on capital intensity and efficiency. If you're application and software, you're competing on differentiation and customer value. And don't assume venture-scale growth. Build sustainable economics and you'll win. Does that capture it?
Perfect. And actually, this is better news than it might sound. In the pure hype phase, everything was overpriced and competitive advantage was unclear. Now that the market is being realistic about what's actually valuable, builders have clearer signals. You're not fighting irrational exuberance. You're competing in a market where people actually care about unit economics and customer ROI. That's an environment where execution and differentiation actually matter. So we covered 20 stories today, and I keep coming back to one observation. The infrastructure is hardening. A year ago, this was all speculation and demos. Now we have frameworks like A.G.E.N.T.I.C that tell you exactly how to build for AI discovery. We have tools, Agent Browser, Colab CLI, QwenPaw, that make AI automation accessible to solo builders. We have governance systems, like Cursor Auto Review, that let you deploy agents safely. The infrastructure pieces are clicking into place.
Right. And what that means is the era of AI is coming someday is over. It's here. It's operational. TCS deploying Claude to 50,000 employees isn't a pilot. It's production at scale. The UK investing 1.1 billion in AI hardware isn't venture speculation. It's industrial policy. The question isn't whether AI matters anymore. The question is, which layer of the AI stack do you want to play on?
And that's where the real sorting is happening. Infrastructure is becoming commodity. Chips, cloud compute, foundational models. Everyone has access to Claude through API. Everyone can train a model for $1,500 now. So where's the differentiation? It's in discovery, making sure AI agents find you and cite you. It's in governance, running agents safely at scale. It's in specialized applications, building workflows that create genuine customer value. That's where the venture returns are.
The long-running agent story was important for exactly this reason. The breakthrough wasn't a new model. It was harness engineering, state files, session management, context rot prevention. That means a solo builder with disciplined infrastructure thinking can build agents that run for days or weeks using commodity models. The leverage isn't model capability anymore. It's engineering and architecture. That's a democratizing shift.
And then there's the elephant in the room. Bots now outnumber humans on the internet. 57% of web traffic is machines. That fundamentally changes how you design any AI-assisted business. You're not just building for humans who click through to your website. You're building for AI agents that crawl, extract, synthesize, and potentially transact. If you're launching a business right now and you're not thinking about agent-first economics, you're already behind. That's probably the most immediately actionable insight from today.
And for traders and strategists watching the AI sector, the bubble versus real infrastructure question has clarity now. OpenAI is at 20 billion annualized revenue. NVIDIA's data center business is nearly 200 billion. Hyperscalers are spending 700 billion on infrastructure and hitting capacity constraints, not demand constraints. That's real. But margins are lower than venture expectations, and the stock market is repricing accordingly. The technology succeeded. The easy money and speculation has passed. Now it's about who executes best.
So what matters most in the coming months? I'd say 3 things. First, watch how discovery and governance solve the agent scaling problem. Can frameworks like A.G.E.N.T.I.C actually help small businesses get discovered by AI systems, or does it require massive brand budgets? That determines whether AI discovery is democratic or concentrated. Second, watch enterprise adoption in regulated industries. TCS's playbook will cascade. Other system integrators will copy it. If those deployments actually work and ROI is real, that's when you'll see AI spending accelerate. Not in generic use cases, but in domain-specific automation. Third, watch the multi-agent collective pathway. The Google DeepMind paper flagged it as underrated. If we start seeing companies build coordinated agent networks instead of single monolithic models, that's a signal the next phase has started.
I'd add one more. Watch what happens with the bot economics. The HTTP 402 paywall protocol is being discussed, but enforcement is the problem. If site owners figure out how to monetize bot traffic instead of getting cannibalized by answer engines, That's a new revenue stream. If they can't, publishers continue to panic, and traffic-based business models continue to collapse. That's probably the most consequential economic shift we haven't solved yet. And for builders, it means your GTM strategy has to account for bot-first distribution from day one. You're not going to get away with ignoring that anymore.
Final thought. If you're launching an AI-assisted business right now, you have real advantages. Infrastructure is cheaper than ever. Tools are more accessible than ever. The hype has deflated, so you're competing on real value, not narrative. Train a model for $1,500. Deploy agents with proper governance. Build for AI discovery from day one. Understand that tokens require atoms. Infrastructure has cost, but it's predictable cost, not venture-scale capital. If you do those things, you're positioned better than 99% of people trying the same thing. That's actually worth something.
That's the right note to end on. 20 stories, but the themes are consistent. The infrastructure is hardening, the economics are clarifying, and the real sorting has begun. Thanks for sticking with us through a packed episode. For everyone building, investing, or trying to make sense of where this all goes, pay attention to discovery, governance, and bot economics in the next few months. Those are going to be the inflection points. And thanks to our listeners for joining us today. This is Tech News Daily. I'm Oliver, with Jane. We'll be back tomorrow with more.
See you tomorrow.